Dear students, welcome back to the 11th week class of Advanced Computer Organization and Architecture. Here I am Aisha Siddiqa, Assistant Professor, Department of CSC. Today we will learn about MIPS Architecture. MIPS means Microprocessor without Interlocked Pipeline Stage. Before going to discuss of instruction set in MIPS architecture, let's know some basic information that you already know or we all of knows like language. So language is the key to understanding of hardware and software interface that you already know. And if you think a program, so a program is executable compiled that is composed of machine instructions. This executable must also run on future machines. For example, each Intel processor reads in the same way, like as the instructions of x86, but each processor handles the instruction differently. If you consider Java programs that are converted into portable bytecode, that is converted into machine instructions during execution, and we know that this is the just-time compilations. And you know about ISA, I mean instruction set architecture. That is the most important design principles for when defining the instruction set architecture. Here is the 2/3 of instruction set architecture. That means the design principle when you defining the instruction set architecture. The first one is keep the hardware simple. That means the chip must only implement basic primitives and run fast. The second one is keep the instructions regular. That means simplifies the decoding or scheduling of instructions. This is the design or geographical view for the MIPS architecture. Here have some important parts like the memory out, address bar, data in, logical control logic, instructions register, and then register file, program counter, and ALU. Here is the registers. MIPS have a 32-bit register, and in here we discuss about the register number with the name of these registers and the description, that means the functionality of those registers. At first you can see the register point is 0, that means the register will be 0 to 31. The first register is 0 and the name of this register is also 0, and the register carrying the value 0. And the second register, that means the register point 1, that is AT, $AT, that means assembler temporary. This is reversed by the assembler. And then 2 to 3 is named by $V0 to V1. That's called values. That means it will be work from expression, evaluation, and function results. Then the register point 4 to 7 is named by $A0 to A3. These are arguments and the first 4 parameters for subroutine. No preserved across procedure calls. And then 8 to 15 that are named by $T0 to T7. Those are temporaries. That means caller saved if needed. Subroutines can use or out saving, not preserved across procedure calls. And then 16 to 23rd that are named by $S0 to S7. That means saved values, call saved. And after that 24 to 25th that's are named by T8 to T9. Those also temporaries and the caller saved if needed. And then after 26 to 27 named by K0 to K1, those are reserved for used by the interrupt or trapped handler. And then 28 that is named by GP, means global pointer. It's point to the middle of the 64K block of memory in the static data segment. and then after the pin number 29, and this is named by SP, which is stack pointer, points to last location on the stack. And then 30, and it's named by S8 or the FP, that means saved value or frame pointer. This is reserved across procedure calls. And the final one is 31, that is named by RA. This is return address. Here is the basic MIPS instructions. If you follow the at firstly, here we example a C code like A is equal to A plus B. That means the value of the variable A and the B and the variable C will be addition, and then the value will assign at A. But in assembly course, this is human friendly but machine instructions, so we can write it like add A, B, C. That means the value of B and C will be added, and then it will assign to A. So A is the sum of B and C. But in machine code, this is hardware friendly but not user friendly. That means it's a machine instructions, and this is the combinations of 0 and 1. That means it's a 0-1 strings. Let's say introduced with operands. That means the variables that we use for any operations. So in C, each variable is allocation in memory. In hardware, each memory access is expensive. If variable is accessed repeatedly, it helps to bring the variable into an on-chip scratch pad and operate on the scratch pad. That means registers. To simplify the instructions, we require that each instruction, that means it only operate on registers. Here the number of operands, that means variables, in C program is very large. The number of operands in assembly is fixed. There can be only so many scratch pad registers. So let's know about the registers. The MIPS ISA, that means instruction set architecture, has 32-bit register that you already know from the previous slide, and it's a processor of x86 has 8 registers. Why not more, but or why not less? So this is a question here, arise a questions, must clear take this knowledge about this question. Okay, each register is 32-bit wide. That means the MIPS register contain 32-bit registers, and each registers of these registers is contain 32-bit wide. The modern 60-bit architecture have 64-bit wide registers. A 32-bit entity, that means 4 bytes, is referred to as a word. To make the code more readable, registers are partitioned as $sign S0 to S7, like T0 to T9. These are temporary variables. What about memory operands? You know, values must be fetched from memory before add, sub, or any other operations. So instructions can operate on them. Like here is 2 steps for take the operands from memory. First one is load word. So this is mentioned by LW $T0. That means then memory address. That means the value from the memory address will be loaded at the register of T0. And the another one is store word. Here the short form of store word is SW T0, then the memory address. That means the value of T0 register will be stored at the memory address. MIPS architecture have 3 types of instructions format, and you know, MIPS has wide 32-bit instructions. So let's know about categories of instructions format about MIPS architecture. The first one is R type, that means the register type, and the second one is I type, that means the immediate type, and then the third one is J type, that means jump types. Let's discuss this briefly in the next slide. At first, R type instructions. So R type instructions refer to register type instructions. Of the three formats, the R type is the most complex. This is the format of the R type instructions when it's encoded in machine code. So every register has 32 bit wide. So this is counted from 0 to 31, that means bit 0 to bit 31. And if you follow the registers or the format of R type, you can see here the at firstly bit 0 to bit 5, that means the first 6 byte will work as a functions, and then the bit number 6 to 10, that means the next 5 is working as a shift amount, and then bit number 11 to bit number 15, those bits are work as a register, that means destination register, register D, and then after from the 16 to 20, those bits are work as another register, that means register T, and then 21 to 25 work as a register S. Here register T and S work as a source register, and register D is the destination register, and finally from bit number 26 to bit number 31 work as a opcode, like add, sub, or anything. So the prototypical R type instruction is add $RD, that means register destination, then the $RS, I means the register source, and then register T, it's a temporary, that means another source. Let's know the details of R type instructions. The firstly is opcode, and opcode is the short for operation code. The opcode is a binary encoding for the instructions. Opcodes are seen in all ISA, that means instruction set architectures. In MIPS, there is an opcode for add. There is another opcode for sub, that means every operations maintain a different opcode. The opcode in MIPS ISA is only 6 bits. Ordinarily, this means there are only 64 possible instructions. Even for a RISC ISA, which typically has few instructions, 64 is quite small. For R type instructions, an additional 6 bits are used, B0 to B5, so called the functions. Those the 6 bits of the opcode and the 6 bits of the function specify the kind of instructions for R type instructions. And then RD, this is the destination register. The destination register is the register where the result of the operations is stored. And then RS, this is the first source register. The source register is the register that holds one of the arguments of the operations. And then RT is the second source registers, and this also holds the one arguments for the operations. And then shift amount, the amount of bits to shift used in shift instructions. And then function, an additional 6 bit used to specify the operations in additions to the opcode. Here is the format of I-type instructions, and I-type is the short form of immediate type. The format of an I-type instruction looks like here also has 32 bits, and the from 0 to 15, that means first 16 bit is work as immediate, and then 16 to 20 work as register T, and 21 to 25th bit of registers is working as register S, and then finally 26 to 31 is working as opcode. The prototypical I-type instruction looks like add register RT, register RS, and then immediate. Here immediate is an immediate value like 5, 10, 15, and RS is a source register that holds a operand value. So here is the operation of add, and RT work as the destination register. So the immediate value and the first source is addition will be adding, and then the value will be stored at the RT. The third instruction is J type instructions, and J type is short for jump type. But now we will skip J type instructions. Maybe we will learn it later in conditional statement are used in our program. Here has some opcodes, and you already know that every operations maintain a different opcode, and the opcode is 6 bits. 6 bits opcode. So when we will go for the practical work or going for exercise of the R type, I type or the J type instructions, then you must know about the opcodes, because without opcode we cannot doing any operations. So it's you need for learning and you need for working. Here have some restrictions for operand addressing that can violate the MIPS architecture instructions. The first one is no instructions for register to register transfer. That means the register to register transfer cannot occur. Then cannot do memory to memory transfer with single instructions. And the final one is SW, that means the store word instructions violates of operands. Please prepare yourself for the next class, and for the next class you must know about the name of registers and the functionality of the registers, and then the instructions format like R type and I type instructions, and finally the opcodes of MIPS architecture. Thank you.